In this video, we will talk about the general addition rule for probabilities, and that looks quite similar to the special addition rule that we studied in the last video, except there's this additional piece that we have to concern ourselves with. Now, the idea behind this is that the probability of two events occurring, or the probability of an occurrence happening in one or another event, while it is equal to the sum of those two events, there is a chance that there's an overlap that occurs with those two events. And if we had event A and event B labeled in a Venn diagram, we don't want to simply add event A, the probability of event A, with the probability of event B, because there's an overlap here in the center of those probabilities. And so we correct that with this additional piece of the rule. Now, what's interesting about this general rule is that it's okay to use for any pair of probabilities or any series of events. And the reason why we don't need this extra piece when we have the special addition or the special addition rule for mutually exclusive events is because in mutually exclusive events, the probability of both A and B occurring at the same time is going to be equal to 0. There's no way that A and B can happen together at the same time in mutually exclusive events. So if this probability came out to be 0, it essentially disappears from the equation, and that's why the special addition rule looks the way that it does. So if we have non-mutually exclusive events or events that have an overlap in probability, then we just have to modify the rule to look like this. So this problem comes from the same section as the others. It's number 4.77. And we're told that Mary Sheridan, a reporter for the Washington Post, wrote about a study describing the characteristics of day laborers in the Washington, D.C. area. And this happened in June of 2005. The study was funded by the Ford and Rockefeller Foundations, interviewed 476 day laborers who are becoming common in the Washington, D.C. area due to increase in construction and immigration in 2004. So these laborers were followed in 2004. The following table provides a percentage distribution for the number of years the day laborer lived in the United States at the time of the interview. So a day laborer is somebody that's hired to do some work. Oftentimes it's not reported as an official employee of a particular company, and therefore goes unreported to government entities. So what we see here is out of the 476 day laborers that were followed, 17% or 0.17 probability of those 476 day laborers lived in the United States for less than a year when this study was conducted. 30% or a probability of 0.30 lived in the United States between 1 and 2 years. 21% lived in the United States for between 3 and 5 years before this study was conducted, and so on, all the way down here to 7%. About 7% of those in this study lived in the United States for 21 years or more. So let's suppose that one of these day laborers is randomly selected. Without using our general addition rule, determine the probability that the day laborer obtained has lived in the United States either between 1 and 20 years inclusive or less than 11 years. So we'll calculate this probability by hand first by looking at the chart, and then later we will try to find the solution by using the general addition rule. So to say that a laborer lived in the United States between 1 and 20 years, according to this chart, would look something like this. So here's the group of laborers that lived in the United States between 1 and 2 years, 3 and 5, 6 and 10, 11 and 20. So this is the group that's between 1 and 20 years inclusive. And then the group that lived in the United States for less than 11 years, well, that would be this group here, and I'll try to highlight that in yellow. We'll see what this looks like. So less than 11 years would be this group. Now, the thing to keep in mind when we use this or phrasing, probability of A or B, this means that that an event that occurs in any of this shaded region can be counted. So the probability that a person selected is either between, or that has lived in the United States between 1 and 20 years or less than 11 years would be the sum of each of these probabilities that have been shaded. Even if they got shaded twice, we'll still only count them once, but if they were shaded even just one time, we do want to include them in the total. So for A, if I was writing this up, I might say that event A is the likelihood that a day laborer has lived in the United States between 1 and 20 years. And I'll say that event B is anyone that's lived in the United States for less than 11 years. And what we're looking for is the probability that event A or B has occurred. So probability of event A or B, well, we know that that's equal to the sum of all of these probabilities. So we have 0.17 plus 0.30 plus 0.21 plus 0.12 and finally 0.13. I can add those probabilities together with the calculator, 0.17 and 0.30 and 0.21, 0.12, and 0.13 all sum to 0.93. So the probability that someone picked up in this study has lived in the United States between 1 and 20 years or less than 11 years is a 0.93 probability, or 93%. Now to answer part B, let's show what this would look like using the general addition rule. The probability of A or B occurring is equal to the probability of A plus the probability of B minus the probability of A and B occurring. So these two are the independent probabilities, and this is the shared probability. And so we need this independent probability of event A. So this is the likelihood that someone has lived in the United States between 1 and 20 years. This is the likelihood of them living in the United States for under 11 years. And this one, where the two overlapped, is the likelihood of both A and B occurring. So they lived in the United States for under 11 years, and they lived in the United States between 1 and 20. So that's the part that got turned into green up here. Now I took the liberty of adding these together already, or obtaining the results. For yellow here, the probability came from just these 4 events. For blue, the likelihood of somebody living in the United States for between 1 and 20 years is from these 4 events. And then, of course, the overlap where the two are shared, that's the green section here. That's the sum of these 3 events. So the probability of A, again, was 0.76. The probability of event B occurring is 0.80. And the probability of A and B occurring, where the two probabilities overlapped in this chart, was 0.63. And the general addition rule says that we would add the two independent probabilities and subtract the intersection of the two probabilities. So we have 0.76 plus 0.80 minus 0.63, and that too equals a probability of 0.93. So thinking about what we had to do to answer this problem, in part A it was very nice for us because we had a table of percentages. This is basically a relative frequency table. And with the relative frequency table, it's very easy to find the overlaps and find the likelihood of two events occurring at the same time. So it was very nice for us. For part B, it was a bit tedious because I had to add together a bunch of these probabilities anyway, just to be able to use the shortcut formula. So I'll leave the answer for C up to you to decide. Which method did you find easier? It didn't say faster, it said easier. Which one do you think would be easier? Do you like using the probability formulas, or would you rather simply read your data off the table and obtain a result from there? Let's take a look at another example. In problem 4.81, we're told that the U.S. National Center for Education Statistics publishes information about school enrollment in the Digest of Education Statistics. According to that document, 84.8% of students attend public schools, 23.0% of students attend college, and 17.7% of students attend a public college. So if we carefully label our events here, we can probably use the general addition rule to answer this final question. So let's go ahead and just say that a student that attends a public school could be event A, and the student that attends college is event B. Now, if that's the case, this question, what percentage of students attend either a public school or college, is asking us to find the probability of event A or event B occurring. And we know from the general rule that this is equal to the probability of A occurring plus the probability of B occurring minus the probability of both event A and B occurring at the same time. And if we read through the word problem, I bet we have this information. So probability of event A, probability that a student attends a public school. Well, we have that here. Here's P of A. Probability of B, a student that attends college. Well, that's this next calculation here. This is probability of B. Go ahead and make it real clear which percentages we're talking about. And then finally, a student that attends both a public school and college. So public college is a public school and college. So that's the probability of A and B occurring. So we have the three parts that we need. We can just fill them into this equation now. Probability of A is 0.848. Probability of B is 0.23, and the probability of A and B is 0.177. So simple math here leads us to see that 0.848 and 0.23 take away 0.177 is equal to 0.901. 0.901. So the probability that a student attends college or attends a public school is equal to 0.901, where there's a 90% chance. Let's take a look at another example. This is 4.82, right after the last one. Suppose that A and B, I think this should say are events. A and B are events such that the probability of A is 1/3, the probability of A or B is 1/2, and the probability of A and B is 1/10. Determine P of B, the probability of B. Well, again, we can use this using our general rule. Probability of A or B occurring is equal to the probability of A plus the probability of B minus the probability of A and B. This looks like the problem that was presented to you on the quiz last week. So the probability of A or B is 1/2. The probability of A is 1/3, and the probability of A and B is 1/10. Our job is to find out what the probability of B by itself is. So I could use basic algebra to solve this here. If I add 1/10 to both sides of the equation, that will allow them to cancel on the right. And if I subtract 1/3 from both sides of the equation, that'll allow these two to cancel. And we would be left with the probability of B is the result of 1/2 plus 1/10 minus 1/3. Now I'm going to do this by hand rather than going to the calculator. I'm going to go ahead and make a common denominator equal to 30. I know all three of these numbers will go into 30. So in this first case, 1/2 of 30 is 15, 1/10 of 30 is 3, and 1/3 of 30 is 10. So basically in my mind I was thinking about what do I do to change this denominator into 30? Well, I had to multiply it by 15. So 2 times 15 equals 30. 1 times 15 is 15. 10 times 3 was 30. 1 times 3 is 3. And 3 times 10 is 30. So 1 times 10 is 10. And the result from this math is our probability of B. So it looks like 15 plus 3 makes 18. 18 take away 10 is 8/30. However, if I record an answer in fractional form, in rational form, it better be reduced to lowest terms. I think we can do better than this, so I'll divide both the top and the bottom by 2, and that leaves me with 4/15. And I think that's all the better we can do. There's nothing that divides both 4 and 15 other than the number 1. So given these three pieces of information, that the probability of A was 1/3 or 1 out of 3, probability of A or B happening was 1/2, and the probability of A and B happening together was 1/10, we were able to successfully identify the probability of B by itself. Go ahead and take a look at problem 4.83 on your own. I'm not going to walk through it in this video, but it does look a lot like the last problem. But it asks us a couple extra questions. For example, are A and B mutually exclusive? And we want you to be able to explain how you know that, whether they are or not. And essentially what that comes down to is, what does the probability of A and B look like? Because if this probability is equal to 0, then we know that they are mutually exclusive. If it's not equal to 0, then they're not mutually exclusive. So if it equals 0, then they are mutually exclusive. So I'll let you do that on your own and tell me what you come up with. I think I'm going to do one more example in another video, so be on the lookout for it.